on that side and on that side.
Okay, so if I multiply T1,
It cancels.
okay, so times T1 times T1. So that's going to cancel those. So that tells me V1, but what am I trying to find?
T2.
Okay,
Multiply V2 to the other side.
so if I multiply V2, if I multiply V2, then my V2 is going to be V2 squared. So do you see the challenge with this? My unknown is in the denominator. All the ones we've done, the unknown has been in the denominator at the top. So in this one, T2 is in the denominator. So what can you do? What is one way if you needed to get T2 all by itself? There's two things you could do. One thing you can do is cross multiply. Do you remember that? Okay. So if you cross multiply, you multiply the denominator on one side times the denominator on the other side, and it'll be equal to the denominator times the denominator on the other side. So by what I mean by that is you would cross multiply. So V1 times T2 will be equal to V2 times T1. Do you remember doing that? And then to get T2 all by itself, what would I do? Divide both sides by what? If I want by, nope, I want T2 all by itself, so I'm not going to touch that. What do I have to move so T2 will be all by itself? Look at the formula. If T2, I want it by itself, what do I have to move? V1. So to move V1, I would divide both sides. And do you see that that would cancel? So V1 and V1 would cancel. So T2 would equal V2 times T1 divided by V1. So if you end up and you have this, the unknown is in the denominator, you can make it so that they're equal by doing that cross multiplying. There's one other way you can do it, and I don't know if you find that this way is easier, but the other thing that you can do is you can flip the formula. So V1 over T1 is equal to V2 over T2. So if I just flip the formula, really? Now you're going to do this? If I'm going to flip the formula, I would just change T1 over V1 equals T2 over V2. So I could just take and flip them. Whatever's in the denominator goes into the denominator and vice versa, because it's still going to be equal to each other because it's the same proportion that's there. And notice in that one, now T2 is in the denominator where I need it. And now the only thing I need to move over is I have to move V2 out of the way. So in this one is just flip the formula. One way that you can get T2 in the denominator, this one is by cross multiplying. And you can do either way. You don't have to do them both. You just do one. But if I flip the formula, do you see that T2 is on the right? I need to move V2, so how would I do that? How do I move V2 over to the left? So I'm talking about this. How do I move V2 over to the left side of the formula? Nope, those all stay. T1 stays, V1 stays. T2 is my unknown. T2 has to be all by itself. That means I have to move V2, so how do I move it? If it's in the denominator and I want to move it to the other side, I have to do what? Multiply both sides by V2. So if I multiply this times V2, multiply this side times V2, do you see that those would cancel? Do you see that the formulas are the same? So you can do whichever one's easier for you. This one still is V2 times T1 divided by V1 is equal to T2. Same thing at the bottom. If I cross multiply and move V2 over to the other side, I guess it's V1 over to the other side. That would be fine too, either one. So my formula T2 is equal to V2 times T1 divided by V1. So in this one, these are two different ways of rearranging the formula. You can cross multiply so that it puts them as equal to each other, or you could flip the formula and then move V2 over to get it T2 all by itself. Whichever one's easier, whichever one makes more sense. But either way, you end up with the exact same formula. Then you just plug in the numbers. So V2 is 22.5 liters. T1 is 300.3 Kelvin. And then divided by V1, which is 52.5 liters. 22.5 times 300.3, 52.5. And I got 128.7 degrees Kelvin. So now before I round this, I want my answer in Celsius. So what do I have to do? Subtract 273. So to go from Kelvin to Celsius, you subtract 273. Remember, this is in Kelvin, so I have to subtract 273. This is going to give me a negative 144.3 degrees Celsius. To go from Celsius to Kelvin, you add 273. To go from Kelvin back to Celsius, you're going to subtract 273. Now I need to round. Once you get to the final answer, that's when you round. So I have 52.5, 3 significant figures, 27.3, 3 significant figures, 22.5, 3 significant figures. So I know my answer needs to be 3 significant figures. So the 1, the 4, and the 4 are my 3 significant figures. So the 3 gets dropped off. Right. So that's just 3 significant figures. Negative 144 degrees Celsius. Okay, so maybe we'll do one more of these next time. So I know the big challenge in this one is trying to figure out how to rearrange the formula when the one that you want to know is in the denominator. So if the unit you want to know is in the denominator, you have to do one of two things. You either cross multiply, which is what I did in this one, which just means you multiply on opposite sides, set them equal to each other, and then you can move the variables. Or you could flip the formula. So I took the V1 over T1 equals V2 over T2 and just flipped it, put T1 on top, V on the bottom, and that way then I could solve for T2 because I had to get T2 in the denominator. So when you go to solve for your unknown, make sure your unknown is in the numerator, not in the denominator in your problem. Okay? All right, so last time we were talking about these attractive forces between molecules. And so the first one we talked about was what are called London forces or dispersion forces. These are when you have small nonpolar molecules that have very little attraction, but when they're big, when you're looking at like 6, 7, 8, 9 carbons, now they become big enough that they actually start to show some attraction. So this one is 2, 4, 7. So this is like heptane. So if you have a heptane molecules, they exist as a liquid at room temperature because they have these very, very weak attractive forces. Little hydrocarbons like methane, propane, they're gases at room temperature because these aren't strong enough to even have an effect on them. But big non-polar molecules may be a liquid at room temperature because of London forces. Then we talked about the polar molecules. When you're talking about a polar molecule, and remember in a polar molecule, these are the things you look for. You look for a nitrogen, an oxygen, a fluorine, or a chlorine. Okay, so remember that those polar molecules, it's always these ones in this upper right corner. nitrogen, oxygen, fluorine, and chlorine. These are the ones that don't share their covalent bonds very equally. So they like to pull the electrons towards them. So looking at that example that's up here, this oxygen pulls the electrons towards it, pulls the electrons towards it. They don't hang out with the carbons as much. They get pulled towards the oxygen. That's why that side becomes a little negative. And that's that little symbol that they like to use. So you can kind of see what that delta symbol, it's the one that's kind of looks like, well, kind of looks like this. And this one's like a little positive on it. Or it might have a negative. So that means slightly. So remember we talked about that in chapter 3. Polar molecules do not share covalent bonds equally, and that creates this slight charge, not like an ion, not like a salt, but a little bit of a charge. And notice how these all line up. So these will line themselves up when you put them in solution. And so this creates attraction. So these molecules tend to be liquid at room temperature, even though they're relatively small. So the polar molecules, they call that dipole-dipole attraction. The third one, though, is a strong type of polar bonds. This, and it's really, even though I told you nitrogen, oxygen, fluorine, and chlorine, it's really, chlorine doesn't really have this ability because it's a little too big. Fluorine, we don't really have very much fluorine in the body. Like there's fluoride, but that's a salt, so you don't have to worry about that one either. So in fact, for living tissues, if you see a nitrogen and or an oxygen, and there's a hydrogen attached to it, then it can do this hydrogen bonding. So if you see a nitrogen with a hydrogen or an oxygen with a hydrogen, then you know that hydrogen bonding is possible. So hydrogen bonding creates an even stronger attraction between molecules, even stronger than just polar. Even stronger than just polar molecules. This is going to create an attraction so that really pretty small molecules end up being liquids at room temperature because the molecules are so attracted to one another. So if you see something like NH3, ammonia, because that nitrogen has the hydrogen, if there's another NH3 molecule near it, that NH3 molecule will set itself up so that the nitrogen will try to get close to the hydrogens of the other NH3 molecule, and they form this attraction. So this attraction that nitrogen has for the hydrogens of the other nitrogen, they're two separate molecules, but now they've got like this link. So they have this connection. It's stronger than just being polar. Anytime you see a nitrogen with a hydrogen or an oxygen with a hydrogen, that means that molecule can do hydrogen bonding. So this is a hydrogen bond. And a hydrogen bond is stronger than just being polar. So if I have a molecule like methanol, CH3OH, because you see an oxygen with a hydrogen, it has the ability to hydrogen bond. So if two of these molecules come near each other, this oxygen is going to be attracted to the hydrogen that belongs to the other oxygen, and that creates the hydrogen bond. The more hydrogen bonds, the more hydrogens that those oxygens or nitrogens have connected, the greater this attraction. So methane, you know, is a gas at room temperature, CH4. But methanol is a liquid at room temperature because of this ability to hydrogen bond. So it's a liquid at room temperature, whereas CH4, this is a gas at room temperature because all it does is London forces. So it's a non-polar molecule. It doesn't have create this attraction. So those molecules want to act like independent. They don't really care about each other. They act as if they're not there. But when you add in an oxygen or a nitrogen in a molecule, that's going to greatly increase its attractive force for other molecules. So that, with hydrogen bonding, that's really all you look for. Hydrogen bonding, look for an oxygen or a an oxygen or a nitrogen. And if there's a hydrogen on them, then they're definitely going to hydrogen bond. So the best example of this is like what water does. So here's how water is such a small molecule, it should be a gas at room temperature, but water has an oxygen with 2 hydrogens. So not only does it want a hydrogen bond with other hydrogens, it's going to allow hydrogen bonding with 2 other oxygens. So you can see, like in this, here's your water molecule. That one water molecule can actually hydrogen bond with 4 other water molecules. So it begins to create, so here is another one. So notice how the oxygen to the hydrogen with this 3rd water molecule, oxygen to hydrogen with the 4th, oxygen to hydrogen all the way around. So all of these, this attraction, this attraction, this attraction, this attraction, this really makes this act like one big molecule. Instead of water acting like little independent molecules, they all want to stick together. So the big one to remember with hydrogen bonding, just look for an oxygen or a nitrogen with a hydrogen attached to it, like H2O, like NH3, like CH3OH. All good examples of polar molecules that are going to hydrogen bond because of this attractive force that occurs if oxygen and nitrogen are involved. And fluorine is too, but we really don't talk about fluorine because it's not found so much in the body. But nitrogen and oxygen do. This hydrogen bonding that water can do creates special characteristics of water that other molecules really don't have. So water molecules, they say that there's 4 major characteristics that water molecules have, all because of hydrogen bonding. So 1, water has a really high melting point and boiling point because water molecules like to cling together. So they like to stay together. So compared to other molecules close to water's size, it's got a much higher melting and boiling point. It takes a lot more energy to break these hydrogen bonds. So this means if you have water molecules, like that previous picture floating around, or like the one that's right here, where I've got 5 water molecules all kind of arranged around each other. If I have this to break those hydrogen bonds, I have to put more energy in. This is why they say water has a very high specific heat. Specific heat is a comparison of how much energy does a molecule or does a sample of any molecule have to have in order for it to change temperature. So because of hydrogen bonding, water has a very high specific heat, which means it changes temperature very slowly. I have to put a lot of energy in for those hydrogen bonds to start getting disrupted for that water to change temperature. This is a good thing for us because remember, we're roughly 2/3 water. That means that your body temperature heats up and cools down very slowly. So like an example is like a pool. So if you've ever had like an outdoor pool without a heater or anything, and you open it up, usually it's like in April, late April, you open up your pool, you put the shock in, you start circulating it. But in May, it's still really cold. Like it takes a lot of time for it to warm up. You have to have a lot of really warm days. Pools change temperature very slow. But your pool now, even though we've had those cold nights, the temperature of the water hasn't changed dramatically. It's going to take a lot of 40-degree nights before the water temperature is going to get too cold. So that's why like the ocean, this time of year, the ocean actually feels pretty warm because it doesn't change temperature quite as fast. That's a big benefit for us because it helps us to maintain a relatively constant body temperature. So water has a high melting and boiling point. Water changes temperature very slowly, and water likes to cling together. So if you've ever looked at like the rain when it falls on your car, like you start off with those little tiny drops, but when those little drops start to slide down the window, you notice they like come together and they make a bigger drop, and those come together and make a bigger drop. So water likes to cling, stick together, and that creates what they call surface tension. So this is supposed to be a water bug. So this is my water bug right here. His little antennae. The water bugs, have you ever seen them like on a stream or out on any kind of surface of water? They look like their little arms and legs are sticking way out. And if you look real close, you can actually see they create almost a dimple or a dent on the surface of the water, but they don't fall in. They don't fall in because they're actually sitting on top of those hydrogen bonds. They're sitting on top of that surface tension. So the reason you can float on water is because of that surface tension. Those hydrogen bonds actually help to hold you up. If you've ever seen somebody water ski or if you've ever water skied, same thing. So you're literally skimming over the surface of all those hydrogen bonds. If you've ever done a belly flop in a pool, it like hurts, right? When your skin smacks the surface of the water, and that is because you actually break the hydrogen bonds of the water on that surface. They say that water has a semi-solid characteristic due to all of those hydrogen bonds. So this stickiness, this wanting to cling together that water has, this can actually cause a problem for premature infants. So one of the last systems to mature for a fetus is the respiratory system. So if a baby is born more than 30 weeks premature, then their respiratory system may not be fully developed. And so they might not make what is called surfactant. So surfactant is normally produced by cells in the alveoli, in the little air sacs of the lungs. Surfactant is kind of like soap. What surfactant does is it breaks up the surface tension, so it keeps water from sticking together. So for a premature infant that doesn't make surfactant, when they inhale, the first time they inhale, they open up the lungs, air flows into the lungs, into those small little teeny tiny air sacs, but without surfactant, when they exhale, the lungs completely collapse. So the lungs will actually close all the way back up. And so then it means the next breath they take, they have to pull those airways back open, and when they exhale, they collapse again. So 15, 20 years ago, a baby like this might not survive because they would get so fatigued. Their diaphragm, their intercostal muscles are so small that they wouldn't be able to force that opening of the airways up. And so a lot of times they go into respiratory distress and then respiratory failure. They'd stop breathing and they wouldn't make it. So they realized that it's because of this stuff called surfactant. So surfactant is kind of like soap. So the best way that I can show you this is to do it as part of a demonstration. So in this is just water. Okay, so what I'm going to do is I'll give you a couple of these. So these are they're just paper clips. They're just paper clips that I kind of folded to make them into kind of like a little flat shape. What I want you to do is this is the paper clip holder. I want you to take the paper clip and see if you can float it on the surface of the water. Just like, I don't know if these ones have been cleaned. I didn't get a chance to clean them before class. Hopefully it's not an issue. What we're going to do, lower it. Okay. Can you do that?
I believe I can.
That. Here's the paper clip, and here's the paper clip holder. Okay. Who else wants to try? Who's willing to give it a shot?
Slowly.
Real slow. It's gotta you're trying to get it so that it floats on top. Yep. And the whole reason that it floats, is because of hydrogen bonding. And if you look at it really closely, can you see that it creates like a dent? Can you see that like on the surface of the paper clip where it's laying, that it makes almost like a little dent on the surface of the water? All right. Dry it off. Okay. You got to set it just like that. Yep. Real slow. Lower it down and in.
You want to let them try? Oh, you got enough?
Do it.
Yes.
Okay. Try that. See if you can do it. Yep. So now I want you to, like, when you look at it though, can you see it's a little dent? Like how on the surface? Which one? Yes. Okay. All right. So you got to get it, like, lay the paper clip right on the paper clip holder so that it's just laying on top, and just slowly lower it down. Just like that. Nice and slow. Lower it down. Right into the liquid. And then look, so can you see how it like looks like it's like there's a little bit of a dent where the paper clip is? The whole reason it stays up. Did you get it? So the whole reason it stays up is because of hydrogen bonding. So you're really doing like what a water bug does. So the water bug spreads it out, and if I had the paper clip flat, it'd fall through. So I bent the paper clip and spread it out so that it's more like how the water bug is. There's hydrogen bonding on the surface of the water and then hydrogen bonding below. And that creates the support so that you can actually hold that up. Okay? All right, so I got one more. And this is oil. You want to pull yours out? This is oil. Oil only does London forces. It does not do hydrogen bonding. So fish it out, dry it, and see what happens when you try to float a paper clip on oil. So this doesn't do hydrogen bonding. Do you need some paper towels now? I was like, okay. The paper one. Okay. I'm going to try to do the same thing. Without hydrogen bonding, there's nothing on that surface. Great. Nope, not like that. That's lay flat. So you tell me what happens when you go to lower it down in. Like as you lower it, tell me, how does the paperclip look different? What does it do? Doesn't it just go right in? Like there's nothing. Like when you put the paper clip, it like floats. And so with this, you go to lower it and it just goes. There is no support. Like it doesn't even start to float. It like drops right in. And that's because oil's mostly carbons and hydrogen. Okay? So oil doesn't do hydrogen bonding. So there is nothing to help hold that up, to help doing that support. So with premature infants, that surfactant, that wanting to cling together, is the reason why your paper clip will float. but it's a problem for preemies because water wants to cling together, and that creates respiratory distress. So what they figured out is they could actually spray surfactant into the airways of a preemie. The surfactant would break up this surface area. And the best way I can show that is just a little bit of soap. Okay, so you're floating. Okay, so if I take one very small drop, what happens? It drops right in. Adding a drop of soap breaks the surface tension and causes the paperclip to just like be able to drop down through, because the soap breaks this up. So we'll talk about what soap does. We made soap in lab. We'll talk a little bit more about how soap does that, but it's the same thing. Surfactant is just like soap. So surfactant's kind of an interesting, it's in like a little can with a long straw. So it almost looks like WD-40, but it is really just like a little aerosol soap. So baby is intubated, so they've got an airway in the baby. They just take this straw, stick it down in the airway and go, give a couple of squirts, and it basically coats the inside of their airways, and it keeps the water from clinging. So just like your paper clip dropped, it causes the water to not stick together, to just line the walls of their airways, and they can breathe. Then they give them steroids galore and keep giving them Yeah, because the steroids is going to help push their lungs to develop faster. So they'll give baby steroids, keep them on a ventilator, and keep giving them surfactant to try and help to ease their respiratory distress, and then wean them off. As their little lung cells start making their own surfactant, they wean them off, and they have less issues. They have less problems, less developmental issues because of that respiratory distress. But that's the whole cohesive thing. Just think like because of hydrogen bonding, water wants to cling. And it clings enough to create that strength to even support that paperclip or a bug or your water skis, all those types of things. Last one. So last one, remember that water, they call it the universal solvent. Okay? So remember that the solvent is the thing that dissolves other things. Well, water, because it's polar, it can mix with things that are polar. So polar and polar mix, remember that like dissolves like that we talked about in a previous chapter. But water also is very good at mixing with ionic compounds. So salts, things like sodium chloride, things that have a charge, because water has a slight charge. That attraction allows water to interact with things that are polar, things that hydrogen bond, and things that are ionic. Really, the only thing that water doesn't like to mix with are lipids, right? Things that are non-polar. So the greases, the oils, the waxes, those are really the only things that are a challenge for water to mix with. Is it still floating? Yeah. So I mean, it's pretty cool. Like it's enough of a force that it can support something like that.
You said oil and what?
Oil and water don't mix, right? So oils, greases, waxes, water does not mix with those. And so we've got to talk about what lipids are like then in the body, because we don't have that mixing to occur. Okay, so we said London forces, then that polarity, dipole. Third one, hydrogen bonding. Fourth one, this one is the fourth attraction. They call this ion dipole. Yeah, oils, greases, waxes, fats, those are all nonpolar, right? And water doesn't like to work with any of them. Water doesn't mix with any of those. Anything nonpolar, water is going to exclude because it has such a strong attraction for things that are polar or ionic. In fact, that's what creates the fourth one. So this one's number 4. They call it ion dipole, and this is what happens when you put salt in water. So if you look at this bottom image, see the sodium ion, right? So this is Na+, the sodium ion. So the sodium is attracted to the water molecule. So is the chloride ion. This is the 4th one.
So the universal solvent, what number 4?
Those are characteristics of water, right? So that's the high melting and boiling point, high specific heat, the cohesiveness, and then the universal solvent characteristic. Those are 4 characteristics of water that are all because of the fact that it hydrogen bonds. And this is the 4th attractive or intermolecular force, right? So this is the 4th way that 2 molecules want to interact. And this is what happens whenever you put salt in water. So if you put salt in water, the sodium will be attracted to the oxygen, because remember that the oxygen has a slight negative. The hydrogens here and here have a slight positive. So it's polar. So because it's polar, sodium is going to be attracted to the oxygen because it's slightly negative to a positive. You know, opposites attract. If you look at the chlorine side, you can see over on the chlorine side, the hydrogens with their slightly positive are attracted to the negative nature of the chloride ion. So again, opposites attract. This is why salts don't stay solid when you put them in water. So if you take a spoonful of salt, put it in water, stir it up, completely dissolves and disappears. That is because the sodium interacts with the water, the chloride ions interact with the water, and they stay completely mixed. So when we talk about things like in the body fluids, remember we had talked about, like we said, calcium +2, chloride with a negative, that there's magnesium +2, potassium with a positive. All of those ions are dissolved in body fluids because they have a charge, and that allows them to interact with water. Whether they're positively charged or negatively charged, water can interact with all of those. And that's why when they talk about your sodium levels, they don't talk about your sodium chloride levels, they talk about sodium levels. Or they talk about your potassium. Or they say like your magnesium is way too low. Okay, they talk about just one of the ions because the ions are dissolved in water because of this attraction. I like this picture. If you look at a salt crystal, all the greens are chlorines, all the purples are sodiums. So you see how salt likes to make this crystal? But if I take this and put it in water, it literally gets disassembled by the water molecules, separated so that the chloride ions surrounded by sodium, the chloride ions are going to be surrounded by hydrogens, the sodium is surrounded by the oxygens of the water to help break it up. This is the last one. This is number 5. Sodium chloride, NaCl, as a solid, so table salt, it melts at 2,500 degrees Celsius. You have to get it really hot, okay? Really hot. So in order to break the ionic attraction, you have to heat it to 2,500 degrees. Water melts at 0 degrees Celsius, 2,500. Most of your salts that you buy, like any kind of salt, whether it's potassium chloride, sodium chloride, even like baking soda, like sodium bicarbonate, all of these have a very high melting point because they are ions. And ions form this very regular kind of crystalline shape where the positive ions are surrounded by negative ions and vice versa. And they have the strongest attractive force, which is why they don't melt very easily. They like to remain a solid at room temperature. So if you have a crystal of salt or a cup of salt and you leave it out, it will stay stay solid permanently because of this attraction of ionic compounds. The sodium ions attracted to those chloride ions. Now you can add water and you can get it to dissolve. So you can break up the attraction, but it doesn't just break up on its own. So salts, very stable solids at room temperature, not to change over time because this is the strongest attraction. So you can always recognize a salt because remember, it's always a metal and a non-metal. Right? So whether we're talking about like iron oxide or potassium sulfide or calcium bromide, if you have a metal and a non-metal listed, then you know the strongest intermolecular force will always be that ionic attraction.
Na plus Cl.
Mm-hmm. Yep, Na plus and Cl minus. So here's like examples of the 5. Weakest to strongest. And what you want to do is just look at like, what are you looking at? How would you identify which type of intermolecular force is the strongest in these examples? So in this first one, notice that it is only carbon and hydrogen. So if it's only carbon and hydrogen, then I know that this is nonpolar. And it's only London forces that help hold this together. Nonpolar molecules, they don't have any other intermolecular forces, just London forces. The next one, if you see nitrogen, oxygen, fluorine, chlorine, okay, and no hydrogen on an oxygen or that nitrogen. These molecules, as long as it's relatively small, we'll say like less than 5 carbons, these are going to be polar, right? So if you have a nitrogen, oxygen, fluorine, or chlorine, no hydrogens on the oxygen or a nitrogen, then this is polar, and that attraction they call dipole-dipole. So like CH3, CH2, double bond oxygen with the hydrogen. So I see that carbon has an oxygen on it. So one oxygen, small molecule, this is polar. Yeah, usually less than 5 carbons. If they start getting bigger, if you start getting 6, 7, 8, 9, 10 carbons, then they might act more nonpolar. But if it's small, then that oxygen is not going to be sharing its electrons equally, and that part of the molecule becomes slightly negative. And you would say the strongest attraction for this is dipole-dipole interaction, is polar. Third one. So the third one is if you see a nitrogen or an oxygen with a hydrogen attached. So in this one, see there's an oxygen and there's an H attached to the oxygen. So if you had an N with an H attached to the nitrogen, then I know that it hydrogen bonds. So this one's an alcohol group, an amine group would all be examples of one. Even carboxylic acids can do that hydrogen bonding. Anytime you have an oxygen or a nitrogen that has a hydrogen directly connected to it. And this is going to create a molecule that's much more attracted to other molecules around it. Fourth one, and the fifth one, okay? Just recognizing an ionic compound. So KCl, potassium's on one side of the zigzag line, chlorine's on the other side. So I know that that is a salt in water. If it's a salt in water, then I know that the strongest force is what they call that ion dipole. Ion being the salt, dipole being the water. So putting that salt in water is the strongest attractive force. And then the last one. So if you just see a metal and a non-metal listed, then you know that this is the strongest of all of the intermolecular forces, and it forms salt crystals. So that's just ionic. So these are the 5 types. London forces, if you see nothing but carbon and hydrogen. Dipole, dipole, if you see a nitrogen, oxygen, fluorine, or chlorine, no hydrogens on those, that's going to be dipole, dipole. Hydrogen bonding, if you see a nitrogen or an oxygen in a molecule with an H attached to it. So it can't just be an H anywhere, but the H has to be connected to the oxygen or the nitrogen. If you see anything in water, pretty much it's always going to be a salt in water. That's that ion dipole. And the last one, if you're just given a compound and the first element's a metal, then you know that it's the strongest of all the intermolecular forces, creating very rigid, solid structures at room temperature. Those are your salts. Those are the ionic compounds. So we'll just practice a few. So everybody got these. These are the ones that you want to use like in doing the comparison. You're looking for those. So like this first one at the top. It's a carbon with 3 hydrogens and a chlorine. So what do you think the strongest intermolecular force is for this? So do you see that? Do you see that that one is dipole, dipole?
Because the H is not on the oxy.
No, there's no oxygen in that molecule. It's a carbon with 3 hydrogens and a chlorine. But remember, nitrogen, oxygen, fluorine, or chlorine is going to create a polar molecule. So I do have that chlorine. So that means that this side is going to become a little negative. This side is going to become a little positive. That creates the polar molecule. Let's go back. Look, read now, dipole, dipole. Nitrogen, oxygen, fluorine, or chlorine. Okay? If I have a nitrogen and oxygen, a fluorine, or a chlorine, if there's no hydrogens attached to those, and really it's the nitrogen and oxygen, then you know it's going to be polar because it's a small molecule, it's polar, and that's dipole, dipole. All right, what about this one? 5 carbons in a row, hydrogens all around. London forces. So London forces is when you have only carbon and hydrogen. So see that there's nothing but carbon and hydrogen in this one. This is London forces. That's pentane. What about Al2O3?
Is that the metal and non-metal?
So this is what? Aluminum's a metal, oxygen's a non-metal, so this is?
The strongest.
Ionic. All right. CH3OH. What's the strongest for this one? CH3OH. This one's a hydrogen bonder. So remember, if you have nitrogen or oxygen, and there's a hydrogen attached, it hydrogen bonds. Okay?
What we got that on the other paper?
Right here. Nitrogen or oxygen with a hydrogen bonded to it. So I have to have a nitrogen with a hydrogen or an oxygen with a hydrogen in order to have hydrogen bonding.
And it's a what?
Hydrogen bonding. Okay? And then what about the last one? So the last one is sodium sulfate, Na2SO4 in water.
It's an ion.
Because that's a salt. Na2SO4 is a salt. Metal in a non-metal group. Salt in water. Ion dipole. So these characteristics really govern whether a sample is a solid, a liquid, or a gas at room temperature, how attracted molecules are to one another. We'll do that one next time. These attractive forces do come into play in the biomolecules. So what is that molecule that you see? Does anybody recognize what this is? What is this? Have you seen this before? It's DNA, right? So do you remember the double-stranded helix, right? So the purple strands create that. This double-stranded helix in DNA is held together. Those two strands are held together because of hydrogen bonds. And so in this, if it'll let me do it, magnify, well, no, it won't. Okay, so if I hold it up, I'm sorry that it's kind of gray, but do you see that in this one that there's an oxygen with a hydrogen, a nitrogen with a hydrogen? There's 3 of them, and you see the little red dots between? So each of those represent the bases that are on opposite strands, and those dots are hydrogen bonds. So now look at the strand. Do you see that every T to A has 2 sets of dots? Every G to C has 3 sets of dots. So you're looking at the length of the strand. So that means every little line of dots, those are hydrogen bonds. So they say that hydrogen bonds are only 10% as strong as a covalent bond. So they're not very strong. But if you look at this DNA molecule, do you see that there are a lot of them? All those little dots is a hydrogen bond. Every 10 is the equivalent of a covalent bond. So that is why the double-stranded helix stays together, because of all of those hydrogen bonds between those bases. So the 3 between G and C, the 2 between A and T, kind of keep that double-stranded helix snapped together. You can pull it apart, but it's going to snap right back up together if they come anywhere near each other because of that hydrogen bonding. And look, now it decided to stay. Now it probably won't go away. All right. Okay. So DNA, hydrogen bonds, proteins take this very 3-dimensional kind of complex structure. Hydrogen, intermolecular forces come into play. There are actually some ionic forces that are there. There are some hydrophobic or nonpolar London forces. There are some dipole. There's hydrogen bonding as well. So there's a lot of those. We're going to kind of mention them again as we go along. And just remember what they call the golden rule of solubility. The golden rule of solubility is like dissolves like. So things to remember, things that are polar, that do dipole-dipole interaction, they like to interact with other things that are also polar. So polar mixes with polar. Things that are polar are hydrophilic. So this term, hydrophilic, means water-loving. So things that are water-loving, so things that are polar, things that are ionic. They like to mix with water. Those are going to be able to mix together. Things that are hydrophobic, the word hydrophobic is like scared of water, because a phobia is a fear. So remember, philic is loving, phobic is fearing. Things that are hydrophobic are things that are not going to want to mix with water, and those are your nonpolar molecules. So sugars, salts, those are polar or ionic. They like to mix, have no problems mixing with water, dissolving in the bloodstream. But things that are nonpolar, so those fats and oils, in digestion, they tend to not mix with water. They're called hydrophobic. So here's an example showing a sugar and how sugar likes to mix with water. So there can be ... oxygen. A water molecule would like interact with any alcohols in the sugar molecule. So see the little OHs hanging off? Water molecules will interact. So since there's so many of them, even though sugar is kind of a big molecule, this is sucrose, it still is soluble in water because of all those oxygens. Oxygens with hydrogens, they can all hydrogen bond, and that allows it to dissolve despite the fact that it's relatively big. This one, I like this picture. I should move it further up because this one actually shows like how water dissolves a salt. So it shows the salt crystal, that's the green and the purple. Water like approaches the salt crystal and it begins to surround and pull the sodium ions and the chloride ions out of the crystal by surrounding them, allowing them to dissolve completely. So this is how you can put salt in water, stir it up, completely dissolves, doesn't separate out, is because the sodiums get surrounded by oxygens of the water, the chlorides get surrounded by hydrogens of water, and that allows them to dissolve and float within the water sample, and it stays mixed. So that becomes this ion dipole interaction. So the last part of this chapter talks about, well, I guess this is one. This is almost all of the drugs that you ingest are absorbed through the GI tract. So in order to get absorbed, they have to be soluble in water. But if you look at something like pseudoephedrine has a lot of carbons. It does have a nitrogen. It does have an oxygen. So these ones, they could hydrogen bond, but there's only two. And by comparison, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So remember I said the bigger the molecule, then the less of an effect those nitrogens and oxygens play. So this is not very soluble in water. It can dissolve a little because yes, there's an oxygen and a nitrogen, but notice all of this that's over here, that's nothing but carbon and hydrogen. So there's a lot of non-polar part to pseudoephedrine. So what they do is they will take and chemically alter a molecule to either add more charge, because if it's got a charge, now it can do ion dipole. Now it can dissolve in water because it can act more like a salt. So pseudoephedrine hydrochloride is a pseudoephedrine molecule that now has an extra hydrogen added to the nitrogen to make it positively charged. So now it's got a charge. So now having that charge, it has an easier time interacting with water. So they say almost half of new drugs that are produced, they're not soluble in water. So they can't get absorbed. So they can alter them chemically to try and make them more polar, to try and make them more ionic, and that'll help increase their ability to dissolve in water. Pseudoephedrine does nothing for me. When I had my cold, when I had COVID, I had a really bad cold, and I was like taking pseudoephedrine every 4 hours, and I was like, this does nothing for me. So I went to the pharmacy and I was like, I want the real stuff. I want the phenylephrine. And so they were like, well, okay. And so like they keep it in the back, you can't actually it's not on the shelf anymore. I took one, totally dried me up for like 12 hours. I was like, wow, there's a difference right there. So it's like different kind of meds just have different effects.
You took what?
So, and I had COVID like 2 weeks ago. I mean, all I had was a bad cold. Honestly, I mean, I felt like I had a low-grade fever for maybe 24 hours. It was the new variant that's out there is not so horrible in terms of symptoms, but it's really infectious. Because I went to a dinner party, 11 people, 6 people got COVID. From half of the people that were in a room together for 3 hours, half of the people in 2 days. In 2 days, 6 people had symptoms.
So you know that's what you got to
I am 100% sure. But I mean, that's really fast.
Yeah.
Like 2 days. But all I had was a bad cold. So I was taking, and it's actually the phenylephrine is the stuff that they put out on the shelf. It's been changed because you can take pseudoephedrine and make crack out of it. Yes. Meth. Sorry, it's meth. Yeah. So you can use it and actually synthesize meth like with it's not a good thing to do at all, but because people started going and like buying boxes of this stuff like and using it to be able to produce illegal drugs. So they changed the formula. So instead of pseudoephedrine now, it's actually phenylephrine so that you can, like if you go buy Sudafed, it's phenylephrine. Does nothing for me. I was taking it for 3 days. I took it and I was still super snotty. So I finally got tired and went to the pharmacy and said, I want the real Sudafed, which is pseudoephedrine. So I got it, took 1 pill, 12 hours. I had no I had like, but you can't get it off the shelf. You have to go to the pharmacy and ask for it. Yeah, it's the old school Sudafed. So Sudafed has 2 formulations now. There's phenylephrine, which you can't make that into meth. So that is the stuff that they just put out on the shelf. Pseudoephedrine is the original Sudafed, but they took it off of the regular shelves because people were using it to be able to synthesize meth. So they still sell it. It's not illegal. They still sell this.
Is that why they have like a lot of medicines like behind the counter?
Yes.
That are still there. You don't even need a prescription to get them, but you have to go and ask for it. And so yes, I went up to the Walgreens lady and I was like, look, I need some pseudoephedrine. And she was like, well, do you want it with this? Do you want it with that? And I was like, no, I just want plain pseudoephedrine. I don't want any guaifenesin in it. I don't have any cough. I don't have, like sometimes it'll have Tylenol in it. Sometimes it has like cough suppressant in it. Now, if you're going to get something with codeine, you need a prescription. Yeah. There's nothing there's no over-the-counter with codeine. That's going to come from a doctor. But pseudoephedrine, it's over the counter, but you have to go to the pharmacy to ask for it. And for me, that like drives me up like, boom, done.
And it's good though?
It just depends. It depends on, like I said, some people phenylephrine, the new Sudafed works fine. Doesn't work for me.
No, it doesn't.
It doesn't work at all. It doesn't.
Old school one for real though.
And it's all you tell them is you just want to have just that. Pseudoephedrine. It's the old Sudafed. And you can get like, they have like the Walgreens version. It's not super crazy expensive, but
I'm going to get that today.
it just like, and for some people, maybe it won't work for you, but this was like, when I finally took it, I was like, wow, I can breathe again. And so I like took it for 2 more days. See, and she said she took Mucinex and it worked great. So it really depends on the person,
I can only do the Mucinex D, the green box.
Oh, really? What's the other one do?
It's D. They have DM and then just the regular.
It doesn't work?
That's the one I use the daytime, nighttime.
Yeah.
Does this make you drowsy?
No, that makes me super wired. I can only take one. I can only take one. Like it says take 2. I can't take 2 because I'm like, yeah, it makes me more loopy than normal. So it just sort of depends. So what about molecules? What about molecules that are polar and nonpolar? Okay. So things that are polar and nonpolar, they use the term amphipathic. So amphi, like an amphibian, is like a frog. It can live on land and in water. So amphi means both. So amphipathic is both hydrophilic or polar. It's going to have an area that's hydrophilic, which is polar or ionic. And it's also going to have a hydrophobic region. So remember, the hydrophobic area is going to be the nonpolar long carbon chain. So it's going to have structures of both. So in lab, we made soap. Soap is amphipathic. Amphi, because, everybody ready? because it has that polar ionic head and the non-polar long carbon chain. Which is hydrophobic. So here is like the little diagram they use. So this one actually gives you the like ball and stick model of a soap molecule. So notice here, over on this end, we have two oxygens, which would be definitely give that dipole, but one of those oxygen is charged. So not only does it have that polar characteristic, it's also got an ionic characteristic. So we have ionic polar head. So this area is the part they call the head just because it's on the end. So they like draw it like a little circle. But then all those going down the chain is nothing but carbon and hydrogen. So this is the long non-polar part of the molecule, which they label a tail. So they say it has a polar or charged head and this non-polar tail. That's what a soap molecule is. So if you take soap molecules, like we made soap, and you put them in water and you like tested its cleaning ability and everything. So what soap molecules do, as soon as you put them in water, the polar heads, the hydrophilic heads, they want to interact with water, but the hydrophobic tails do not. So they wrap themselves into a sphere. So in the sphere, remember that this part is hydrophilic. This is the head. So all the hydrophilic heads are all on the outside. And then the hydrophobic tails tuck into the center to get away from the water, because remember, water doesn't mix with things that are non-polar. Hydrophobic things and hydrophilic things don't want to mix. So this is why you end up with this sphere. The heads are all on the outside. Tucked into the inside are those non-polar tails. This is a soap molecule. Soap molecules, they form this structure, which is called a micelle. So first thing to remember is that you must have water. So this is in hand washing. You wet your hands, okay? You can't just use soap. Soap by itself does not form micelles. Soap by itself is going to make like a paste. It's going to make kind of like a layer, it's going to feel greasy because of those long tails. But as soon as you add water and begin to mix, so you have to first wet your hands. 2, you add the soap molecules. So whether your soap is liquid or solid, doesn't matter. You mix for 5 to 10 seconds, and it takes 5 to 10 seconds of mixing to form millions of micelles. This is a micelle. You get millions. So on your hands, you wet your hands, you add soap, you start scrubbing. 5 to 10 seconds. You should really notice bubbles. You really notice like your hands like that lathers up. Sometimes it even starts looking kind of cloudy. So that is telling you you're making millions of these micelles. That's what's forming on the surface of the hands. Now, if you have things on your hands that are polar, hydrophilic, ionic, if you have salts, if you have sugars on your hands, that stuff just mixes with water and it's going to wash away no matter what, right? So you don't really need soap. If you just put salt on your hand and put your hands under water, it would dissolve in the water and wash away. But what about the non-polar stuff? Have you ever gotten grease on your hands? If you rinse it in water, nothing happens. Your hands are still greasy. You can't just use water because the oils will stick to your hands. They will not dissolve in the water. They're going to cling to your hands. That's why you use soap. So, 3, after 5 to 10 seconds, you have, please just After 5 to 10 seconds, anything that is non-polar, so hydrophobic, molecules, and this could be grease, could be oil, waxes, it could also be bacteria. And the reason I mention bacteria is because bacteria have a waxy, oily coating that helps them to stick to stuff. So the reason that bacteria actually sticks to your hands is because bacteria have a surface coating that's called a lipopolysaccharide layer. So it's got this greasy layer that helps it to stick. So if you just rinse your hands and there's bacteria on your hands, they are not coming off. But if you use soap, anything hydrophobic will go into the micelles. So oils, grease, fats, bacteria, they're attracted to the hydrophobic interior of the micelles because they're also hydrophobic, like dissolves like, right? So things that are nonpolar hydrophobic go into the micelle because inside of the micelle is nonpolar or hydrophobic. That acts to actually lift these things off of the surface of your skin. Anything that's hydrophilic is just going to dissolve in the water, right? So the hydrophilic doesn't really care if the soap is there. But most of your like stains, most of your compounds, most things are not pure substances. Most of the time it's a mix of it. So if you have some oily, greasy stuff and you have some salty, sugary stuff, using the soap is going to help to break it up because the soap is going to get the grease and the oil to go into those micelles. So hydrophilic, right? So hydrophilic, the water-loving hydrophilic molecules will dissolve in water. Doing this takes another 10 seconds, 5 to 10 seconds. So it doesn't happen instantly. That is why when they say you wash your hands, you do the 20-second hand wash. 20 seconds because it takes about 10 seconds just to make micelles. It takes another 10 seconds to try and get things to break up that's on the surface of the skin so that when you're done with this, the very last thing you do is you rinse your hands. Everything that's in the micelle washes away. Everything that's dissolved in the water washes away. And this is how you can effectively clean your hands. Does that make sense? That's kind of the premise. It's really the premise behind hand washing. It's really chemistry. It's just because of what soap molecules can do. So next time we will finish chapter 7 and start chapter 8. So for Wednesday, make sure you get the pre-lecture for chapter 8 done. There was a gas law. Wasn't there a gas law thing done? It wasn't listed?
I made my sugar. As you see, I've been doing my mastering.
Mm-hmm.
You see it?